Hi everyone, myself Dr. Lakshmi Prasad, working as a professor in CSC in Institute of Aeronautical Engineering, Hyderabad. In this video, I'm going to discuss about the topic like introduction to differential equations and numerical integration. So basics of differential equations. So here I'm going to discuss what are the basic terms we have to be remember in differential equation. So the very first thing is that ordinary differential equation. So ordinary differential equation is nothing but an equations involving a function of one independent variable and its derivatives. Okay, so an equation involving a function of one independent variable and its derivatives, what we called as a ordinary differential equation. Initial value problem. So initial value problem means an ordinary differential problem that specifies the value of the solution at any particular point is nothing but initial value problem. Okay, so initial value problem means an ordinary differential problem that specifies the value of the solution at a particular point. And boundary value problem means it is an ODE, that means ordinary differential problem, so which is going to specify the values of the solution at the boundaries of the domain. And linear differential means that it is an ODE where the dependent variable and the derivatives appear linearly. Okay, it's an ordinary differential equations where the dependent variable and its derivatives appear linearly. And non-linear means it is an ordinary differential equation where the dependent variable or its derivatives appear non-linearly. And next one, order of an ODE means that the highest derivative of the dependent variable in the equation. Highest derivative of the dependent variable in the equation is nothing but the order of the ODE. And next one, there are two different types of ordinary differential equations. So first one is homogeneous ordinary differential equation. So homogeneous means that so in this where every term is a function of the dependent variable and its derivatives. So we're normally able to set to zero. A non-homogeneous ODE, an ODE that include the terms that are not the functions of the dependent variable and its derivatives is nothing but inhomogeneous ordinary differential equation. Right? So these are some of the basic terminologies we have to be remembered in differential equations. So an equation which is going to involve the function of independent variable and derivatives is nothing but the ordinary differential equation. And these two will be the types of this, so homogeneous and non-homogeneous. Homogeneous means where every term is a function of dependent variable and its derivatives are going to be set to zero here. And non-homogeneous means that it includes the terms that are not the functions of the dependent variable and its derivatives. An initial value problem, adenoid differential problem that is going to specify the value of the solution at a particular point, and boundary value means that which is going to specify the values of the solution at the boundaries of the domain. And linear, an ordinary differential equation where the dependent variable and its derivatives are going to appear linearly, where the derivatives are going to appear non-linearly, is called as nonlinear ordinary differential equation. Some other methods are going to see now. So what is separable ODE? So an ODE, that can be written as the product of functions of the independent and dependent variable, which is going to be separated into signals, is nothing but separable ODE. An ODE that can be written as the product of functions of independent variable and dependent variable. And Euler's method. So Euler's method is nothing but a simple numerical method for solving ODEs by approximating the solution using tangent lines. Okay, a new simple numerical method for solving ODEs. Now, approximating the solution using tangent lines is nothing but Euler method. And Ramthunda method is nothing but it should be a group of iterative methods for solving ODEs with the fourth order being particularly problem. And stiff ODE means an ODE with the solutions that exhibit rapid changes, so requiring specialized numerical methods for stable solutions. An ODE with the solutions so that exhibit rapid changes requiring specialized numerical methods for stable solutions is nothing but stiff ODE. And phase plane, so a graphical representation of trajectories of a dynamical system in the plane of two variables. So typically it used for second order ODEs. So a graphical representation of trajectories of a dynamic systems in a plane of two variables. So typically called as a second order ODEs. And a concept that is going to be determine the stability of equilibrium points in dynamical systems is called stability. An analytical solution is so the exact solution of ODE which is going to be expressed in closed form of expression is nothing but analytical. So separable ODE means an ODE that can be written as the product of functions of independent and dependent variables. And Euler method means a simple numerical method which is going to be solved ODE by approximating the solutions using tangent lines. And Ranirathunda method means a group of iterative methods for solving the ODEs and with the fourth order Ranirathunda method by particularly popular. And stiff ODE means an ODE with the solution which is going to exhibit rapid changes, so requiring specialized numerical methods for the stable solutions. And phase plane is nothing but a graphical representation of the trajectories of the system in a plane of two variables, so typically used for second order ODEs. And life horn of stability means a concept that is going to be determine the stability of equilibrium points in dynamical systems is nothing but life horn stability. And analytical solution means the exact solution of ODE, so which is going to be expressed in the form of an expression. So first definition is the differential equation. So a differential equation is an equation which is going to contain the derivative of one or more dependent variables. So with respect to one or more independent variables. So differential equation is nothing but an equation containing the derivative of one or more independent variables. So with respect to one or more independent variables. So suppose if I'm going to consider dy by dx, that should be equal to 2xy. Otherwise, I can also write dou u by dou x. And x into dy by dx is equal to 1 minus 1. And d square x by dx square and d by y by dx plus y equal to 0. And dou x plus dou x by dou y plus dou y by dou x plus 2 equal to 0. So these are now some examples of this differential equation. So differential equation is an equation which is going to contain the derivative of one or more dependent variables with respect to one or more independent variables. So there are different types of this differential equation. First one is ordinary differential equation and second one is partial differential equation. So ordinary differential equation means an equation contains one ordinary derivatives of one or more dependent variables of single independent variable. An equation contains ordinary derivatives of one or more dependent variables of single independent variable. So that is dy by dx plus 5y is equal to 3x. And dx plus dy plus dy by dt is equal to 2x plus 1. So an equation which is going to contain only ordinary derivatives of one or more dependent variables of a single independent variable. And dy by dx is equal to dy by dx plus 5y is equal to x, and dx by dt plus dy by dt is equal to 2x plus 1. And partial differential equation. So an equation that contains partial derivatives of one or more dependent variables of two or more independent variables. So the equation contains partial derivatives of one or more dependent variables of two or more independent variables. So let it be dou square u by oh, dou square u by dou t square is equal to u dou u by dou t, and dou u by dou x equal to minus of dou u by dou x. So this ordinary differential equation means an equation contains only ordinary derivatives of one or more dependent variables of a single independent variable. And partial differential equation means an equation that contains the partial derivatives of one or more dependent variable of two or more independent variable. In this, we are going to see different types of order of ODEs. So first order differential equation is the equation which is going to involve unknown function y and its derivative what we called as y dash and the variable x. So we will only talk about the explicit in differential equation. So if I'm going to consider the equation as y is equal to x comma y, and general form is going to be write it as dy by dx is equal to x comma y, and the function is going to be subject to 2x plus y equal to 3. So 2x plus 3 equal to 0. So y is this. And what are the applications of this ODE means that, so while modeling, if I'm going to consider, so I'm going to make use of this modeling, so we can able to extract the Newton's law of cooling and electrical circuits, and then modeling free mechanical oscillations like this if I'm going to take. So you can able to take no damping and then light dampening and like heavy dampening. So the modeling of forced mechanical oscillations and computer results are going to be active. So what are the examples of this of first of all? So in these examples of PDE, so we're going to see about Laplace equation, or we're going to estimate this and heat equation, and then some other equation. So normally this one, this PDS is going to be used to model. So this PDS is going to be used to model many systems in many different fields of science and engineering. So importance of important examples is that, so the PDs are going to be used to model many systems in many different solutions of complex engineering. So important example is the Laplace equation, heat equation, and the wave equation. So what is this Laplace equation? So the Laplace equation is going to determine the steady distribution of heat in the body, and it is also going to be used to describe the steady state department distribution of electrical change in the world. So Laplace equation is going to use to describe the study of the state distribution of heat and body. So if I'm going to consider this Laplace equation, so it is going to have any kind of equation. Heat equation. So the function u of x comma y comma z, it is going to use to represent the temperature at any time t in a physical body at a point with coordinates of x, y, z. So the function mapping of x, y, z is going to be used to represent the temperature at time t in the physical body at point with coordinates. So lambda is the thermal feasibility. It is sufficient to consider the case like alpha is equal to 1. So the function u x y z is used to represent the temperature at time t in physical body, and alpha is the thermal diffusivity. So it is sufficient to coordinate the case alpha is equal to 1. So dou u by dou x of x y z of t is equal to dou square u by dou square by dou square mu square by dou y square minus mu square u by dou x square. So these are now will be the Wheeler's Thomas and model that is going to be used to represent this. And next one is wave equation. So the function u of x y z is going to represent the displacement at a point, and the constant c is going to be represent the propagational speed of the wave. So that is rho square u by dou x y z by t is equal to c square into square u by dou x square underscore u by dou y square underscore u by dou y square. So implementation of this, I'm going to consider be about various applications of this ordinary differential equation, and some of the examples of ordinary differential equation is the Laplace equation, heat equation, and all of this. So Laplace equation is going to use to describe the steady state of distribution of heat in the body, and it is also going to be used to describe the steady state distribution of electrical change in the body. And next one is that basics of numerical integration. So basic terminologies in numerical integration is that, so a method that is going to be export approximate the interval of a union. So a method that will approximate the integrity of the function. The trapezoidal rule, the numerical integration. So it is nothing but a method to approximate the integral of a function when an analytical solution is difficult or impossible to obtain. So it involves the computing of some of the functional value at a specific point multiplied by the weights. And trapezoidal moves a numerical integration method that approximates the integral by summing the areas of trapezoids under the curve. And Simpson's rule is also same. So a method to approximate the integral by fitting the parabolas to segment of the curve and then some of their areas. And next one is quadrature. So quadrature is nothing but the process of determining the integral function using numerical methods. So a technique which is going to approximate the integrals using the weighted sum of functional values at specified points. So this in the then they providing high accuracy for polynomial. Okay, a technique that is going to be approximate the integrals using weighted sum of fraction values at specific points, providing high accuracy for the polynomials. And then Romberg integration. So it is nothing but an interactive method which is going to improve the accuracy of trapezoidal rule using Richardson extrapolation. So an iterative method which is going to be improve the accuracy of the trapezoidal rule using Richardson extrapolation. An adaptive quadrature is nothing but a method that is going to adopt the interval size, so based on the function behavior to achieve a desired accuracy. So adaptive quadrature is nothing but a method that is going to be adapt the internal size based on the functional behavior to achieve the desired accuracy. And the midpoint rule, so an integration method that is going to approximate the area under the curve using midpoint of the checkpoint. And the next one is that Newton's Cotes formula. So if a group of families for a group integration, so based on the polynomial interpolation and the trapezoidal rule and Simpson rules, I'm going to do that. So in our exam also they are going to ask these problems, trapezoidal rule and Simpson's rule. So basic integration is that. So an interactive method that improves the quality of the trapezoidal rule using interpolation. And adaptive quadrature means a method that is going to be adapt the internal size, so based on the functional behavior to achieve the desired accuracy. And midpoint rule is that so integration method approximates the area under the curve using the midpoint of each interval. And Newton course method means that a group of formulas for numerical integration, so based on a polynomial interpolation, so including the Simpson's rules and the trapezoidal. So what is this numerical integration? So it is nothing but a branch of calculus which is going to be deals with the functions that is going to be integrated. Okay. So it is nothing but a branch of calculus which is going to be deals with the function to be integrated. And integration is nothing but the reverse process of differentiation. And function to be integrated is nothing but is going to has integrator which is going to be result of an integration is called integral. So the integral is equal to the area under the curve. So integration is nothing but the reverse process of the right angle. And the function is going to be integrated is referred to as integrand, which is going to be result of an integration called integrals. So normally the symbol what I'm going to use is this one for denoting the sum, which is going to be denoted by lean lineage, so which is named as integral calculus. So this calculus and somewhat onions, so these two would be the basic. And this numerical integration is going to be carried by the numerical method, and then say they are going to have three different types. So in numerical integration, there are two types like definite integrals and indefinite integrals. So definite integrals is going to be defined by the limit values and b of the independent value. Different integrator and definite integrator is that so all the integrals which with no requirements as so integration that is not going to be improved as it has independent variables. So here I'm going to represent it as integrated f of x dx. So with the limits of a and b. So normally also can able to represent f of x dx. So what is this trapezoidal rule? So it is an applicable for equal intervals, and then the error is of order of height h2, and the error is an order of improved integration by increasing the number of intervals and decreasing the value. In this rule, the y of x is linear to x, so in general, the trapezoidal rule is less than this when IQ pure of x. So in this rule, the y of x should be the main function. In general, I'm going to. So in general, so the trapezoidal rule is less accurate when compared with the Simpson's rule. So this trapezoidal rule is going to be applicable for equal intervals only, and that that in that the error of the y should be x square, and then the accuracy of the time is and then the number of intervals decreasing the value. And the next one is Simpson's rule, so it is also going to be known as Simpson's 1 0, and it is going to be applicable for equal intervals. And here the address are going to be, so in Simpson's rule, so it is also known as Simpson's 1/3 rule, and it should be applicable for equal intervals, and the error should be order of h power 4, and in this rule the approximate degree should be 2, and it is also going to as 3 data points. And then Simpson's second rule is that, so in Simpson's second rule, so it is also going to be called as 3 by 8 rule, and the order should be of the error order should be 5. So in this rule, the xy should be a polynomial of degree 3. So there is a difference between this one and this one. So it is going to be observable for the intervals which should be which should be multiplied. So in this rule, the y of x is the polynomial of the degree 3, and it is going to be applicable for intervals which should be a multiple of 3, and it is also going to be used here 4 data points. So trapezoidal rule. So trapezoidal rule is going to be derived by the formula of f of x naught by xl, and f of x is equal to x is equal to this, and which is going to take a naught for the interval from f naught y naught to ym, and Simpson's rule is going to be defined by the equation f of x naught f x sum by f of x plus f of v dx. So in this, the interval should be by 2 by 4 to 3 to 1. And Simpson's rule second rule is also same, so it is going to have the integration pattern now going to be self distribution. So f of x dx is equal to h by 8. So f of f naught y naught plus yn should be that, and 3 into y1 plus 2 into y, then the function is going to be as 3h by 8. So here is some more basic constraints or parameters you're going to consider, like s naught should be initial value, and should be initial value, xn should be final value, xn should be final value. So here the interval distance is equal to h is equal to p minus a by, and n should be the number of intervals. And what are the applications of this numerical integration is that, so it is going to be helps in finding the area and locating the centroid, finding the arc graph, and then also the surface and so finding the area is one of the application, and locating the centroid is another application. And then can you able to find the arc length of the graph and the arc length of this surface length of the solid, and then some of the for old origin or old work done. And some of the other examples is that is also going to be used in sectional area, water plane, and submerged graph, and longitudinal dimension graphs like this. So these are some of basic applications. Numerical integration. So some of the basic terminologies what I explained right now is that numerical integration, and then trapezoidal rule, Simpson's rule, and then quadrature, and then Gaussian quadrature. In this, some of the basic is that, so Romberg integration, adaptive quadrature, midpoint rule, and Newton's core formula. So normally this is the branch of calculus which is going to be deal with the integration, and integration is going to be done in the process where the function is going to be incorporated as integrated, and then where polling is equivalent to the integral equivalent to the area under the curve. So the integral symbol is going to be elaborate as well. So here a numerical integration is also going to be carried by numerical methods, and there should be three methods like Differential, Simpsons, and Simpson's second rule. Numerical integration we have two types, definite integrals and definite integrals. So definite integrals is going to be defined by limited values, say empty by the integral value, and an integration with integral with no restrictions imposed on the definite integral. And trivial rule, so it is going to be used for numerical intervals and average should be of order 6. And in this rule are going to be find out the x naught. So the rule y of x is the mean function of x, and then the trivial rule less accurate when compared to the Simpson's rule. And Simpson's first rule, so it is also known as one-third rule, and it should be applicable for the equal intervals, and the order should be h power 4. And Simpson's second rule, the order should be h power 5. And these are some of the basic equations where I have to remember this. So in trivial rule, so we're going to get the function Simpson's first rule and Simpson's second rule. So here the x naught should be the initial value x, and x and y and should be the final values of this. And some of the applications of numerical integration means finding the area, location of the centroid, find the outlet length, and the volume of solid figure, and then solve the moment of the, and these are the applications of numerical integration. So it is going to be used in sectional water plants and most likely. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.